earlier in this chapter, we learned that the blood pH value should be between 7.35 to 7.45. pH values below 7.35 will cause a medical condition called acidosis, and any pH value above 7.45 will result in alkalosis. Both of these conditions are potentially dangerous and may be life-threatening in some cases. Yet, both hydronium and hydroxide ions are continuously absorbed and released into our blood from foods we eat and are produced by cells during normal metabolism. Then how it is possible to prevent the fluctuations of the blood pH value? The answer is that blood and many other aqueous solutions are buffers. A buffer is a solution that resists the changes in pH when small amounts of acids and bases are added. So because blood is a buffer, so any change of hydronium ion or hydroxide ion which goes into the blood plasma, it does not cause any difference in the pH value because buffers do not let the pH change when small amounts of acids and bases are added. So this is how the acid-base homeostasis works to prevent acidosis and alkalosis. So what it means is that because our blood plasma is a buffer and buffer pH remains constant, so let's imagine in this case the pH is about 7.4. So if we add small amounts of acid means addition of hydronium ion. Because it's a buffer, pH will not change. pH remains same. And even if we add small amount of base, so addition of base means addition of hydroxide ions. In that case also, buffers resist the change in pH, or in other words, even if we add small amounts of acid or a small amount of base, pH will not change and it will remain constant. And that's how our blood pH remains within this range, and normal healthy humans do not suffer from acidosis or alkalosis. A buffer solution is composed of a weak acid and its conjugate base in similar concentrations. For example, we can prepare a buffer by mixing a weak acid such as acetic acid. So this is the formula of acetic acid. And in organic chemistry, the real formula of acetic acid is this way. So that's the acetic acid, and its conjugate base is acetate ion, which is CH3COO negative. That's the conjugate base. So if we want to prepare a buffer, so what we will do is we will take acetic acid and we will mix it with its conjugate base, which is acetate ion, and only anion cannot be the mix, so it will have a cation also. In this case, the cation can be sodium, but sodium is just a spectator ion. It doesn't really play any part, but this mixture will be a buffer. Sodium just stays in the solution. It doesn't play any part. Now, pH range of the buffer depends on the identity of the weak acid. It could be anywhere from pH 1 to pH 10. So any pH is possible depending on what weak acid you take. So this buffer is known as acetic acid acetate buffer because it's made up of acetic acid and acetate. There are many other buffers are also available. Another important property of buffer is the buffer capacity. Buffer capacity means how much acid or a base can be added to the buffer before the pH will change. So buffer capacity actually represents the ability of buffer to resist the change in pH, or how much acid or a base it can absorb before it reaches to the breaking point. Some common laboratory and physiological buffer solutions are listed here. We already saw the acetic acid and acetate ion buffer. Carbonic acid and hydrogen carbonate buffer is the one which maintains the pH of our blood. So it's made up of carbonic acid, another weak acid, and its conjugate base, which is carbonate. It's found in extracellular uh, areas. And another common lab as well as physiological buffer is the dihydrogen phosphate and hydrogen phosphate buffer. Let's see how a buffer solution works. As we learned that buffer solution is made up of a weak acid and its conjugate base together in a aqueous solution. So for example, if we make a buffer with a weak acid such as HA, so we add a bunch of acid molecules in this aqueous solution. Remember, it's a weak acid. Also, we added similar amount of its conjugate base, which is A negative. So this mixture will, because it's a weak acid, will create an equilibrium reaction, which is shown here. So weak acid will combine with water to give us some hydronium ions and conjugate base, and because it's a reversible reaction, so conjugate base will combine or react with hydronium ion to give us back weak acid and water. So this will be the equilibrium process in which we will have some reactants and some product composition together. It's never going to be 100% on the product side or 100% in the reactant side. So it will be a continuous back and forth process. And we know that in all reversible reactions, Le Chatelier's principle states that if we uh, destroy the equilibrium or if we alter the equilibrium, the reaction adjusts itself to create a new equilibrium. For example, if we add acid to this solution, so if we add more acid, adding acid means we are adding more H3O positive. So adding more H3O positive, what will happen according to Le Chatelier's principle, it will increase the rate of reverse reaction. So it will move the reaction equilibrium to the reverse direction. So reverse direction means that whatever extra H3O positive we added, those H3O positive will combine with A negative to give us back the reactants. So in doing so, the solution essentially removed whatever we extra H3O positive were added. So those were removed by shifting the equilibrium to the backward direction. So if any extra H3O or any extra added acid was removed, so pH will not change. So that's how this buffer will resist the change of pH while addition of acid. Let's review this process one more time. So buffer is created by a weak acid and its conjugate base, and it will establish this reversible reaction. If we add extra acid to it, in any other case, addition of extra acid will lower the pH, but not in this case, because what will happen is that when we add acid to it, we are essentially adding more H3O or hydronium ion. More hydronium ions means that the equilibrium will shift to the left side, and any extra H3O which we added will combine with A negative to produce reactants. So those extra H3O positive will get dissipated, or they will be removed. So therefore the concentration of hydronium ion will change very little, so resulting pH will be the same or almost the same. So hence the pH will not change when we add extra acid. So now what will happen if we add base to it? So addition of base means, so let's remove the addition of acid part. So when we add base to it, so addition of base means now we are adding OH negative. So that's what happens when we add base. So this hydroxide, when we add this to the buffer, the hydroxide will combine with the hydronium ion because they neutralize. So what will happen, that we will have loss of hydronium on this side, because now the base is neutralizing our hydronium. So loss of hydronium means now we have a negative depression on the product side. So according to Le Chatelier's principle, the equilibrium will shift to the right. When the equilibrium shift to the right, more hydronium ions will be produced, and whatever we lost in during the neutralization of base, those hydronium ions will be replenished because now the equilibrium has shifted more to the right. So again, in this, very little H3O concentration change will happen, and resulting pH will be the similar what it was before, and hence the pH will not change. Because of these shift in equilibrium, the buffer solution's pH remains constant. The primary buffer which maintains the pH of blood is the carbonic acid and hydrogen carbonate buffer. This buffer is made up of carbonic acid, which is a weak acid, and its conjugate base, that is hydrogen carbonate ion. The equilibrium reaction between the carbonic acid and its conjugate ion is shown in this reaction. The concentration of hydrogen carbonate ion is regulated by kidneys, which release and absorb this ion as needed into the circulation. Carbonic acid, on the other hand, is a weak acid, and it is formed in the reversible combination of carbon dioxide and water. Carbon dioxide is the metabolic byproduct of various cellular activities. Carbonic acid plays a central role in maintaining the pH of our blood. We saw that carbonic acid is formed when carbon dioxide combines with water. It is a reversible reaction, and according to Le Chatelier's principle, if there is more carbon dioxide in blood, it will shift the equilibrium to the right, and we will get more carbonic acid generated in the blood. This will come in handy when we explain how the buffer action maintains the pH of blood. But for now, just remember that this is a reversible reaction and it follows the Le Chatelier's principle. Now we also learned that there is another equilibrium between the carbonic acid and its conjugate base, which is hydrogen carbonate ion, and this hydrogen carbonate ion is maintained or regulated by kidneys. So it can be removed or can be added into the bloodstream depending on the requirement. So the pH of the blood is maintained by these two reversible reactions and the equilibrium between them. For example, if our blood has more carbon dioxide, which may be formed due to increased metabolic activity, it will shift the equilibrium to the right. That means we will have higher concentration of carbonic acid in our blood. That will result a shift of equilibrium of this second reaction to the right. It means we will have higher concentration of hydrogen carbonate, which can be then regulated by the kidneys. Now let's see what happens when more acid or a base is added to the blood, and these acid and base component may come from metabolic activities or food or from any other source. But let's see what happens when these two acid and base components go to our bloodstream, how blood maintains its pH, because as we know that addition of hydronium ion should decrease the pH and addition of hydroxide should increase the pH. But because blood is a buffer and it maintains its pH between 7.35 to 7.45, and that constant pH is due to the equilibrium reactions as shown here. So let's see what happens when we add more acid to our blood. Addition of acid to our blood means now we have increased concentration of hydronium ion. So hydronium ion goes up. So because hydronium ion has increased on this side, according to Le principle, equilibrium will shift to the left. So adding hydronium ion or acid causes a shift to the left, which means now we have high concentration of carbonic acid. So if carbonic acid concentration is high, according to Le principle, now the equilibrium will shift further to the left. So that means now there will be more carbon dioxide in the blood and more water in the blood. Having more water in the blood doesn't cause any problem, and the increased amount of carbon dioxide in the blood causes lungs to exhale more, so we will breathe heavily or faster, and exhaling more means, or breathing faster will get rid of that extra carbon dioxide from the blood, and hence the pH will be maintained, or pH will stay the same. Let me repeat this one more time. So if we add more acid, so add acid, addition of acid means now we have increased amount of hydronium ion. So whatever extra hydronium ion we added, it will shift the equilibrium to the left. So extra hydronium ions will be consumed and they will produce carbonic acid. Now because we consumed any extra amount of hydronium ions, so the concentration of hydronium ions remains the constant, so pH remains same. Now, but we do have extra carbonic acid, and that we need to get rid of. So how we'll get rid of, how our blood get rid of extra carbonic acid? Then the other equilibrium reaction comes into play. Extra increased concentration of carbonic acid means that the equilibrium will shift further to the left, means that now we have higher concentration of carbon dioxide and higher concentration of water in blood, and increased concentration of carbon dioxide can be removed or can be lowered by our lungs, because it can be exhaled during the breathing. So all we need to do, or all our body needs to do, is exhale more or breathe heavily, and our blood pH value will be lowered or maintain the same. Okay, so now what happens when we add base to our blood? Addition of base means now we are adding more hydroxide. More hydroxide means that whatever hydronium ions we had in our bloodstream, so those hydronium ions will combine with hydroxide to form water. So it means the base will remove hydronium ions from our blood. So there will be a loss of hydronium ion. So adding OH negative decreases the hydronium ion. So this loss of hydronium ion will shift the equilibrium to the right. Shifting this equilibrium to the right will replenish the loss of hydronium ion, and hence concentration of hydronium remains the same. So if concentration remains the same, pH remains the same. But we have now lost some of our carbonic acid. Now, because the equilibrium has shifted to the right, so carbonic acid concentration went down. So in order to maintain this concentration, this first reaction equilibrium now will shift to the right. Shifting to the right, it means now we are losing or decreasing the carbon dioxide concentration from our blood. And to avoid so because of that decrease, all we need to do is, or all our body needs to does is that our lungs to exhale less carbon dioxide. Exhaling less carbon dioxide means that breathing should slow down. So that happens automatically. So our body will lower the breathing rate, and that will maintain the pH of the blood if any base is added to the blood. So with these two processes, or by just breathing heavily or breathing slowly, our body is able to maintain the pH of the blood within this healthy range of 7.35 to 7.45. One thing I should like to clarify here, that you guys may have seen advertisement on TV about alkaline water. They sell special water to maintain the pH. That water does not do anything to our blood. First of all, the water does not go to our blood. When we drink that water, it goes to our stomach, and stomach contains concentrated HCl. So that water does nothing, first of all. Secondly, as you know, that even if there is any change in pH, or any acid or base is added to the blood, our blood is well, or our body is capable of maintaining the pH. So there is no need to drink that special alkaline water. So that's just a gimmick, or a false advertisement to make people think that they are doing something healthy. So with that, we conclude chapter number 9. In this chapter, we learn about acids and bases. We learned about their definitions and their properties. We also learn how we measure the strength of an acid or a base by using a parameter called pH. And we discussed the acid-base neutralization reaction. And finally, we learned about buffers, in which we also learned how the pH of our blood is maintained by a buffer action. Thank you everyone for watching the video. If you have any question, let me know. Have a wonderful rest of the day. Bye bye.